Now we have the innovation from Pakistan by Mohammad Suleiman, and F from PIC Peshawar team for TAVI.
Bismillah ar-Rahman ar-Rahim. I'll be presenting a very interesting innovation, TAVIAssist. It is developed by Structural Heart team at Peshawar Institute of Cardiology, which is led by Dr. Ali Raza. As you all know, that TAVI is a minimally invasive procedure to replace aortic valve. And this TAVI device needs to be implanted at a particular target depth. If we are too deep, it can lead to conduction abnormalities. And if we are too high, the valve can pop out and embolize. So these leave the operator with a very minimal margin of error, just 3 to 5 mm. So in order to achieve this very precise depth, the TAVI device needs to be implanted in a view where this annulus appear in a single line, in a single plane, just perpendicular to the fluoroscopic projection. All those angles in which this annulus appear in a single line can be denoted with the help of an S-curve shape graph. This red line here shows all those angles, a pair of angles in which this annulus will appear in a single line. Not only that, we also need this TAVI device to be in a single plane. So if both this device and annulus are in a single plane, then only we can assess this depth accurately. But there are few problems with this. The first one is that the operator usually remember few angles like 3-cusp view or cusp overlap technique, and he cannot remember this whole graph by memory. So deviation from this is very common, as operator usually rotate its machine into LA or other projection for confirmation of other parameters. The second problem is the problem of parallax. So what happens that these self-expandable devices tend to position itself along the outer curve of aorta. So this leads to a different plane of this device than the annulus. So if you position your machine to bring annulus in plane, the device will go out of plane. If you rotate your machine to bring device in plane, the annulus will go out of plane. So this is the problem of parallax. The third issue is that the patient position during CT scan and fluoroscopy is different, especially in obese patient. So this S-curve, which we usually generate using the CT scan data, can have some errors, and there might be some discrepancy with this fluoro and CT data. So as per our patent search, we could not find any software which can solve all these problems in cath lab on table in real time. So here our solution, TAVIAssist. So this software consists of two parts actually. The one is TAVIAssist, which we install in a computer, and it is the main brain. And the second part is fluoro tracker. As the name suggests, this fluoro tracker is actually track the position of the C-arm gantry or this fluoroscopic machine. This is a mobile software, and we attach this mobile to the fluoroscopic gantry, and when it moves, it gives the current location of that LA or cranial projections over Bluetooth to this main software for further processing. In this video, as you can see, this fluoro tracker is attached to this C-arm gantry. When this is moving, it is sending the location of this particular angle over Bluetooth to this main software, where you can see on this graph there is a dot. It is moving and it is giving the current position. And this is the second part. The main brain is the TAVIAssist. It consists of multiple sub-modules. I will only discuss a few of them for the sake of time. So broadly, we can categorize the function in two categories. The first one is generation of that S-curve. We can generate this S-curve using CT scan data. All you need is any free software. Just get the lowest point of the cusp and get the XYZ value, which any free software can give you. You take these values and put it into our software, and it will give you this S-curve shaped graph. And if you don't like this graph because of the positional change or any other reason, you can also make this S-curve on the table using fluoroscopy data. All you need is to just adjust your angles in such a way that you see a single plane. Just with a single click of button, that fluoro tracker will send the position, and our software will make a graph for you. The second function is that nobody likes to read graphs, especially during a procedure. So we can also track this graph if required. So as you can see in this bench study, this is a phantom of aortic annulus. And our software has generated using fluoroscopy data this S-curve shape graph. At this particular moment, this dot is not on top of this S-curve. So our annulus is out of plane. Sorry. Can you play this video? Video play kar de zara. See what happens when this dot, when the operator move the machine, when this dot come on top of this S-curve, then you get alignment of this annulus. There is another problem too, that problem of parallax. In most of the patient, the TAVI device and the aortic annulus are not in the same plane. So two different plane means two different S-curves. The point at which these both lines cross each other is the point when there is no parallax, and this is called double S-curve technique. It is invented by Dr. Nicholas Piazza. As you can see at this moment, the dot is not on top of any line, so at this point both structure were out of plane. So when this dot come on top of this cross point, the parallax has been removed and both structure are in plane. So this is the most ideal position to deploy the wall. And for those of you who don't like graphs, we also provide this opportunity where you import this CT scan data, the segmented 3D aorta, and import into our software. The software will show you this patient CT 3D rendered aortic root, and when you move the machine, it will show you the current position of this aortic root. So the question is, does it really work? These are very busy slides, but let me quickly tell you here that for the tracking of C-arm position during fluoroscopy, the mean angle error was 0.2 degrees. And for the generation of S-curve and double S-curve and tracking it, the error was again less than 1 degree. So it was very precise, it very precisely generated and tracked that S-curve. This is our comparison with other software. So in summary, our software is different from the other ones because they are all used for pre-procedure planning, while the other software is used during the procedure for real-time assessment of all these parameters. This is our patent information which we have recently filed in US, and this is our future goal. First of all, we want to make a complete CT scan analysis software. At the current in the market, for example, the 3-Mensio, etc. are very costly. 3-Mensio costs £23,000 per year. We also want to integrate into artificial intelligence into our software, where this 3D CT data will be fused over top of this fluoroscopy. And we will also incorporate other important marker like coronary ostia, membranous septum, its depth, and commissioner alignment in real time. Thank you very much.
So